This video will introduce you to the origin and maintenance of a cell's resting membrane potential. While we will be focusing on the resting potential of a neuron, keep in mind that all cells in the body have an electrical potential that exists across their cell membrane. As mentioned in the previous slide, all cells have a membrane potential. A membrane potential is simply a separation of charge across physical space. In this case, the separation of charge is maintained by the cell membrane. Keep in mind that ions can't cross membranes unless a specific transport protein is available to move them across the membrane. So consequently, the separation of charge creates a voltage or a membrane potential across the membrane. This change in membrane potential can actually be used to allow certain ions to cross the membrane down their concentration gradient or by simple diffusion. Conversely, there's also going to be scenarios where we will pump ions against their concentration gradient using active transport in ATP to establish ion gradients. And we've seen this before last semester in the case of both cell respiration and photosynthesis, where cells were generating ion gradients across membranes. We weren't measuring the concentration difference across the membrane, but we were focusing on the fact that a potential difference, an electrical charge difference across the membrane could be used to do work inside of the cell. So the gradient that is established across the membrane is due both to the concentration of ions as well as the charge of the ions, and consequently what we're going to generate is what's called an electrochemical gradient. The electrical gradient is going to be established by the charge on the ions that are separated across the membrane, and of course the chemical part of the gradient will be determined by the concentration of each ionic species on either side of the membrane. Some tips to remember as we begin to work through this. In general, the concentration of sodium ion will always be higher outside of a cell, including most neurons, and the concentration of potassium ion is going to be higher on the inside of the cell, including most neurons. And we can see that generally depicted in this image. So, in the case of the nervous system, the resting potential refers to the cell's membrane potential at rest, or when it is not conducting a nerve impulse, when it has not initiated or propagated an action potential. And we call this the cell's resting potential. As I mentioned in the previous slide, the inside of the cell will always be negatively charged relative to the outside of the cell, and generally the magnitude of a cell's resting membrane potential is around negative 70 millivolts. This is not a hard and fast rule for every single cell that exists in your body, but it's a general measurement of magnitude that works for most scenarios. So if the inside of the cell is negative and the outside of the cell is positive, how has that actually come to be? Well, one of the ways that has come to be, and there are other ways that we will see in a moment, is due to the activity of the sodium-potassium pump. Hopefully at this point you remember the function of the sodium-potassium pump. It is to pump both sodium and potassium ions against their concentration gradient to the inside or the outside of the cell. In the case of sodium ions, of course, 3 sodium ions are being pumped out of the cell, while 3 potassium ions are being pumped into the cell. And if you think about that for a second, what we're going to be creating is both a concentration gradient in the case of sodium ion and potassium ion, but we're also going to be creating an electrical gradient. Since sodium and potassium both have a positive charge, you might ask yourself, how is it possible to establish an electrical gradient? Don't I need both positive and negative ions to establish that gradient? But you really don't. If you move 3 positives out, but you only move 2 potassiums in, there's a net movement of positives to the outside of the cell of 1. So the outside of the cell will have 1 additional positive charge compared to the inside. If you don't like to think about it that way, think about it in terms of negative charge. If I move 3 sodiums out, and I only replace it with 2 potassium ions, which are also positively charged, there's going to be a net negative of 1 on the inside of the cell compared to the outside. So due to the activity of the sodium-potassium pump, along with some other mechanisms which we'll see briefly, the cell's membrane potential is kept at a negative potential for most of the cell's life. So when we look at the distribution of ions across the membrane, of course it's not just sodium and potassium ions that are important. They're probably the most important when it comes to understanding the cell's resting membrane potential, but they're not the only ions that exist on the inside and the outside of the cell. Along with sodium on the outside of the cell, we're also going to find chloride ion. On the inside of the cell, we'll find our potassium ion, and we'll also find A-. Now you might ask yourself, what in the heck is A-? Well, A- refers to all of the negatively charged molecules on the inside of the cell that allow the cell to have a net negative charge on the inside. These molecules might be the conjugate bases of weak acids, they might be negatively charged proteins, they could be other negative ionic species that exist in very small concentrations, but in general it refers to negatively charged molecules on the inside of the cell. Okay, so those are the general ionic distributions across either side of the cell membrane. But along with the distribution of the ions, we also have to take into account the permeability of those ions across the membrane. Remember, ions can't cross the membrane by themselves. They're charged species, and the hydrophobic interior of the cell membrane prevents those ions from crossing the membrane easily. However, if there are transport proteins available, then we would expect those ions to be able to cross the membrane down their concentration gradient. So if you look at the image over here, we can see that potassium ions are diffusing out of the cell, while sodium ions are moving into the cell. And that makes sense because each of those ions will be moving down their concentration gradients. But look at the thickness of each of these arrows. Notice that the potassium arrow is much thicker than the sodium arrow. And what this is referring to is the permeability of each of these ions. The potassium ion has a higher permeability than the sodium ion does for movement across the membrane. This is due to the fact that there are simply more potassium ion channels out on the cell membrane than there are sodium ion channels. More channels, more ionic movement, higher the permeability. Don't forget about your sodium-potassium pump, which is moving those ions against their concentration gradient using energy from ATP hydrolysis. So as sodium ions are moving down or into the cell, that concentration gradient difference is being reestablished by sodium ions moving out of the cell, and as the potassium ions are moving down their concentration gradient and out of the cell, they're being replaced by the sodium-potassium pump as it moves potassium ions back into the cell. Okay, so the next piece of the puzzle is to begin to understand how neuroscientists measure the potential difference across the cell membrane. And perhaps the easiest way to think about this is to think about the giant squid. The giant squid is enormous and has some of the largest axons known to humankind. In fact, you can actually see single axons without a microscope from the giant squid. And scientists early in the 20th century began to exploit this phenomenon and insert very small electrodes or microelectrodes into the cells of the giant squid. And since the axon is really just an extension of a single cell, they began to insert those electrodes into the axon of these giant squid. They would also have an axon in a fluid that was bathing the axon of the giant squid, so that they would be able to measure the potential difference across the membrane. And that might look a little bit like this. Of course, this is entirely oversimplified, but there would be an electrode that's inserted into the cell, there would be a reference electrode on the outside of the cell, and then a recorder that would be measuring the difference in charge or the difference in voltage across the cell membrane. We can see our magic number of -70. That is, again, the typical resting membrane potential of the majority of cells in our body. So why is this important? Well, this is important because scientists began to realize that not only could they measure the resting potential of a cell, but they could manipulate a cell's membrane potential by changing the ionic environment on either the outside of the cell or the inside of the cell. So in the chart on the screen, you see some of the typical concentrations of ions that are found on the inside and outside of a typical neuron. Down below are the human ion concentrations, but you're going to see that they don't differ too dramatically from what you find in the giant squid. Well, what I'd like you to do is begin to practice manipulating the ion concentration on either the inside of the cell or the outside of the cell, and see how it influences a cell's membrane potential. I'm going to show you how to do that on the next slide. On this slide, you're going to find the Nernst equation, and the Nernst equation is an easy way to calculate the equilibrium potential for a particular ion on either side of a cell membrane. So the formula is quite easy to use. E is the equilibrium potential, R is going to be your gas constant, T is temperature, Z is going to refer to the charge on the ion that you're working with. Keep in mind that if you're dealing with chloride ion versus sodium ion, that Z is going to have very different values. If you're not sure what Z is, in the case of sodium, it would be +1. If you're not sure what Z is supposed to be in the case of chloride, it would be -1. And F is going to be a constant. It's Faraday's constant. You can find all those values by quickly Googling them if you so desire. Then what I want you to do, though, is I want you to go back to that previous slide and plug in some of the different ion concentrations on the inside and outside of the cell, respectively, and find out what the equilibrium potential is for a couple of different ions at different ion concentrations. I want you to do this because what you're going to find is that there's going to be a particular membrane potential at which the movement of the ions is going to be the same in both directions. In other words, the movement of that particular ion will have reached equilibrium across the membrane. This is going to be really important because what that equilibrium potential means is that if by chance we were to set the cell's voltage to a particular value, a particular magnitude, then there would be no net movement of that particular ionic species across the membrane. Thus, there would that in reference to that ion, the cell, if it were set at that equilibrium potential, would not allow for a net movement of ions across the membrane. This is going to be really important to us when we begin to explore action potentials, because there's not surprisingly going to be points along the action potential, or the propagation of the action potential, in which we reach equilibrium potentials, in which there's no net movement of a particular ion across the membrane. So at this point, what I encourage you to do is go ahead and practice a few of those calculations. There's really no need to check your work because I trust that you can plug numbers into a formula and get some values. You'll see some questions down here that are worth thinking about. So at this point, go ahead and practice a little bit, and if you have questions, please let me know.